In this lesson, we're going to put everything we've learned about exponential and logarithmic expressions and functions, and we're going to put that together to solve exponential and logarithmic equations. In this example, we have log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. We're going to go back to our condensing and expansion techniques and condense the left side of the equation. So we're going to take this more complicated side of the equation that has all of the logarithms, and we're going to rewrite that to be something more simple. Log base 5 of x plus 6 times x plus 2 equals 1. And then I can further expand that, or condense that, simplify it, to be x squared plus 8x plus 12. Now what I'm going to do, now that I have a logarithm equals a constant, I'm going to write this in exponential form. So we'll write in exponential form. So we're going to take our base 5, raise it to the first power, and that's equal to x squared plus 8x plus 12. Our last step is going to be to set the equation equal to 0 and solve for x. So 0 equals x squared plus 8x, subtract 5 from both sides, and we get plus 7. I'm going to factor and use the zero product property, and I get x equals -1 and x equals -7. My last step, which is the very most important step after you get through all of this algebra, is to check your solutions for those that may be extraneous. Extraneous solutions are solutions that are created in the process of you solving that aren't really solutions. So extraneous solutions are solutions that are generated in the process of you working through the algebra that aren't really solutions. So for instance, when I come back to the original problem, my argument x plus 6 has to be positive. My argument x plus 2 has to be positive. If I put a -1 in, so if I put a -1 in for x, -1 plus 6 is positive. It's 5. It works. If I put -1 in to the next argument, -1 plus 2, that's also positive. That's +1. That works. However, if I put in x equals -7, -7 plus 6 is -1. This is extraneous. It is not allowed. It was generated. Now you might ask yourself, how did that happen? Well, first we're going to say x equals -1 is our solution. That's the solution. If we are asked for extraneous solutions, then we would say x equals -7. But if it just says solve, our answer is x equals -1. So where did the -7 come from? Well, the -7 came from, in the original problem, we had linear. So this was linear arguments. So linear arguments, both of them were linear. X plus 6, x plus 2, those were linear arguments. However, when we condensed our logarithms into one logarithm, what happened? We created quadratic argument. And a quadratic argument produces, in the process of solving a quadratic, two possible solutions. So the linear arguments would have produced potentially one, whereas the quadratic that was generated in our algebra produced a second equation or second solution that wasn't a true solution. Now sometimes that quadratic argument does produce two valid solutions, but not always. So we always have to check for those extraneous solutions. Okay, here's another example. And in this example, it's really helpful to know that if you have log base b of x, and that is equal to log base b of y, so you're given an equation where you have a logarithm on the left and a single logarithm on the right, and they both have the same base, then their arguments are equal. Now, please don't confuse that with this left-hand side being fine the way it is, because it is not one single logarithm. We first need to get a single log on each side. So we need to condense that left-hand side. We're going to use the product rule, and we'll have the natural log of x times x minus 4, and that's going to equal the natural log of x plus 6. I'm going to simplify that. Natural log of x squared minus 4x equals natural log of x plus 6. I'm not sure that's really simplifying. It's probably just multiplying out distributive property. And then we're going to now be able to say I have a single logarithm on the left, a single logarithm on the right. They both have the same base. Therefore, x squared minus 4x has to equal x plus 6. So we'll set this equal to 0. X squared minus 5x minus 6 equals 0. I'm going to factor. I'm going to have x minus 6, x plus 1, x equals 6, x equals negative 1. When I plug 6 back in, it's allowed in the first logarithm. 6 minus 4 is positive. It's allowed in the second. And 6 plus 6 is 12. That's positive. It's allowed in the third. If we try x equals negative 1, works in the last one, it fails in the middle one, and it will also fail in the first one. But if it fails anywhere, then it's extraneous. So our solution is x equals 6. If we are asked for any extraneous solutions, these are not part of these solutions. So when it said solve, the only solution is x equals 6. If it asks us what are the extraneous solutions, that would be x equals negative 1. And solving logarithms is kind of interesting when you know your properties. So when you get that practice in, and you can expand and you can condense your expressions, you can use your going from log form to exponent form. It really makes it kind of interesting to see where do we use it. Well, we use it in solving. Here we have log base 4 of log base 2 of x plus 1 equals 2. So I always start from the inside out. So inside out. In this case, I can't do that because I'm stuck here in the parentheses. So there's nothing there for me to get to. So going from the inside isn't going to be very helpful this time. So I'm going to start from the outside and try going in. So the outside would be 4 squared. And then that's going to equal the argument of log base 2 of x plus 1. So the outside in this case is going to be the way to go. However, now I can take, let me just simplify this to be a 16 so I don't get confused. Now I can say 2 to the 16th power is equal to x plus 1. And 2 to the 16th power Goodness gracious, 2 to the 16th power. I think I might need a calculator for that one. So if I go over to my calculator and I put 2 upper caret 16, I'm going to get 65,536. And then I'm going to subtract that 1, and I get 65,535. And that's what x is equal to. Now I'm going to check to make sure that it doesn't cause a problem. When I put that back in, I get a positive argument. And 2 raised to any power is going to be positive. That's going to give me that bigger number of 65,536. So yeah, so that's going to work. So check, 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 check. It works. And this is where we need our calculator. So 2 to the x equals 5. 2 to the x equals 5. Let's estimate what our value is. 2 to the first power is 2. 2 squared is 4. And 2 cubed is 8. We want to know 2 to what power is 5. It's going to be between 2 and 3. So we expect our answer to be between 2 and 3. I'm going to write this in log form. So I'm going to actually do this problem 2 different ways. I'm going to write in log form. So I've got log base 2 of 5 equals x. And then I can go over to my calculator and I can enter this into the calculator however I want. I can use log AB, or I can say the log of 5 divided by the log of 2, or I could say the natural log of 5 divided by the natural log of 2. And when I put that into my calculator, I'm going to get approximately, it's going to be between 2 and 3. So try putting that into your calculator. And you should get 2.322. About 2.322. Definitely don't skip over that. Make sure that you know how to get 2.322 out of your calculator. Now another way, this is an alternate way. Most professors in later math classes are going to not solve this using this form. They're going to say, well, I learned, that's what they're going to say. They're going to say, I learned to just take the natural log of both sides. So back here, this rule right here, see this rule right here? They're going to say, well, I've got x equals y. I'm going to go backwards and I'm going to log both sides. So they're going to make 2 to the x and 5 arguments. So they're going to say, well, natural log both sides. So you natural log both sides, and you get that. Right? Well, I can write this, the natural log of 2 to the x equals natural log of 5. And then this x comes out front, and we get x. Let me move this over here. We're going to get x out front times the natural log of 2 equals the natural log of 5. And then the natural log of 2 is just some number. So we'll divide both sides by the natural log of 2. And look at that. You get x equals the natural log of 5 over the natural log of 2. And you put that into your calculator. Hooray. However, on a test that I potentially give you, if you do the math this way, that's absolutely fine. But then you're going to have to use your change of base formula to say, okay, that's a log. My base in the denominator, the argument in the denominator is my base of my logarithm, and then the argument in the numerator is the original argument, log base 2 of 5. That's an exact answer. And we know that no matter how you put that into your calculator, you're going to get about 2.322. That's a pretty cool thing. Pretty cool thing. Okay, let's try. See, we're getting close to the end. Let's try, before we move on to these other problems, because they are important problems. Let's just try 2 to the x equals 16. Let's try that as an example. Then maybe let's try 25 to the x plus 1 equals 125. So let's try those 2 problems. When you know those mathematical facts of your exponents that we've talked about in the past, you see these problems in a different way. You say, I don't need to pick up my calculator because 2 to the x has a base of 2. 16 has a base of 2 as well. It's 2 to the 4th. And when you see that, you see right away that x equals 4. No need to pick up a calculator. Second problem here with the 25 and the 125, same thing. You see that 25 is a base 5. And this is very important for you to be able to do on the left-hand side. I'm going to show you. And 125 is 5 cubed. They both have a base 5. So 5 raised to the 2x plus 2. That's right. You're going to multiply, and that 2 gets distributed, equals 5 cubed. Now that they have the same base, the exponents are set equal to each other, and we get x equals negative 1/2. No need to pick up a calculator. No need whatsoever to pick up a calculator. And that's the big thing here, is that we don't need to use very large numbers. We need to be able to do this type of math with smaller numbers without a calculator, so that you can really make sure that you understand the process of what we're going through. So, couple of doozies are coming up. There's a couple of doozies coming up. We've got this problem right here that's going to require a calculator. We've got number 6 that's going to take a lot of algebra and a calculator at the end. And then we've got number 7 that talks about factoring, which I love factoring. And then number 8, which is another little bit of a doozy algebraically. So we're going to come back in another video, and we might even have more after that. One more after that, we do. So we're going to come back in another video, and I'm going to hit these more challenging problems so that you're not completely overwhelmed by one video.